Hi, guys. It's Miss Hernandez again. Good morning, good evening, good afternoon, whenever it is you're watching. Thank you for watching. Today's topic is 6.1 Early History of the Periodic Table. I am working with fifth period again. They're going to be helping me record. Thank you, fifth period. You guys are awesome. And let's get started. So, early history of the periodic table. Everything has a history, even the periodic table. This topic for today talks about the first attempts to organize elements. And of course, they were failures, okay? They have nothing they are related, and they did use some of their information to create today's periodic table, but overall they're not considered. Stop. Oh, my husband's home. Uh, Daisy, hold on, my husband. Go, babe. Open the door. All right, sorry, guys. Okay, so today we're going to be talking about first. The introduction is going to be about libraries and how you are able to locate books. Um, After that, we're gonna go into the early history. Sorry, but one of my dogs was stuck on the bed. All right, who's gonna read?
It is a fiction book. You look by author. Since the fiction materials are filled by the author's last name, if you're looking for a nonfiction publication, you look in a catalog, most likely on a computer. These days, the book you're looking for will have a number by the title. The number refers to the Dewey Decimal System developed by Melville in 1876 and used in over 200,000 libraries throughout the world. Another system wide use in the Library of Congress approach developed in the late 1800s, early 1900s to organize the materials in the Federal Library of Congress. This method is one of the most widely used ways to organize libraries in the world. Both approaches organize information so that people can easily find what they are looking for. Chemistry information also needs to be organized so we can see patterns of properties in elements.
Thank you, Alexia. That's excellent reading. Now, anytime you go into a library, there's a ton of books, right? So the librarian uses a system that was created in the late 1800s by known as the Dewey Decimal System. And the Dewey Decimal System, if you've never used it, and I know you guys probably take advantage of the fact that the Dewey Decimal System, the catalog, the list of books that are in there are now in computer. I know when probably Miss Garza and I were in school, we had to go through a bunch of cards to find our books, and it was a long process, and there was a lot of cards that you had to look through. But you guys are lucky. There's now a lot of technological advances, so you have all the catalog, all the list on computer, and all you have to do is post or write in there, a subject like the history of, I don't know, the history of World War I, and all the list of books that are based on World War I can come up. Okay, so you have a lot of advantages that we didn't have when we were in school. But why are we talking about this system of organization? The reason why we're talking about it is because elements in the early days, as more and more elements were discovered, two people in particular, tried to organize these elements. Okay, and in order to, hey Kevin, in order to so that you can see the similarities and the differences between the elements as far as chemical and physical properties. Okay, so that's the topic for today. How was the periodic table organized in the beginning? So early attempts to organize elements. By the year 1700, only a handful of elements had been identified and isolated. Several of these, such as copper and lead, had been known since the ancient times. So there were some elements that had been around for thousands or hundreds of years. As scientific methods improved, the rate of discovery dramatically increased. So all of a sudden, people were doing a lot of research, a lot of experiments, and one person was saying, "Oh, I found an element." Another person was doing research and saying, "I found an element." Another person was doing research, "I found an element." So all of a sudden, we had knowledge of all of these elements, but we had no system in place that would organize all of this information so it was easy for people to use and understand. With the ever increasing number of elements, chemists recognized that there may be some kind of systematic way, to organize elements. The question was, how do we do it? Okay, how do we do it? So there was two people who attempted to organize these elements, and that is who we're going to be talking about today. A logical way to begin grouping elements together was by chemical properties, right? In other words, putting elements into separate groups based on how they react with other elements. And the first person to try to do that started out in the mid or early 1800s, and he was a German chemist known as Johann Dobereiner. And what he did is he placed various groups of three elements into groups called triads. Okay. Now, an example of one triad is the grouping of lithium, sodium, and potassium. Now, how were these triads grouped together? It was based on physical and chemical properties. All right. These triads were based on both physical and chemical properties, right? How they react with other elements. Dobereiner found that the atomic masses of lithium, potassium, and sodium were, as well as other triads, they formed patterns. Okay, what particular pattern? Well, when the atomic masses of lithium and potassium were averaged together, 6.94 plus 39.10 divided by 2, it equaled 23.2, which was approximately equal to the atomic mass of sodium, 22.99. These three elements also displayed similar chemical reactions, such as vigorously reacting with members of another triad, chlorine, bromine, and iodine. Now, those elements, that's like group 1 with group 17. So why do they like to come together and react? Well, group 1 has one electron that it's trying to get rid of, while group 17 is saying, "Hey, give me that electron. I need one more." Why? Because the magic number is always 8. So if group 1 gets rid of that one electron and gives it to group 17, they'll both have 8 electrons in the outer orbital, meaning that they'll be very, very stable in comparison to where they were at before. Okay, so group 1 and group 17, they're besties. They like to come together because they are able to even each other out. Okay, that's one of the reasons why they react together all the time. While Dobereiner's system would pave the way for future ideas, there was a limitation. Okay, there was a reason why it's not used. Okay, and the reason why it's not used today is because the triad system was not was that not all of the elements could be classified and grouped in threes. Okay, so yes, it was a good idea to group them together by chemical and physical properties, and it might have worked for some elements. It did not work for all elements. That's why it was not accepted. That's why it's not used or accepted now. After Dobereiner, we had English chemist John Newlands. John Newlands, he tried to order elements by increasing atomic mass, and he noticed that every eighth element would show similar properties, right? Similar chemical and physical properties. So he called it the law of octaves. And right now, it doesn't explain why it's the law of octaves, But in the video later, you'll see why he chose that name. Unfortunately, there were some elements that were missing, and the law would not hold. It wouldn't work for elements that were heavier than calcium. Okay. Newland's work was largely ignored and even ridiculed by the scientific community in his day. It wasn't until many years later that another more extensive periodic table effort would gain acceptance, and the pioneering work of Newlands would actually be appreciated. So when he was doing all of this, when he was presenting it to his peers, people were like, no, this doesn't work for elements after calcium. What you're doing, it's not working. Nah, we're not going to use it. And some people even made fun of him. Some people were mean, even back then. And here you have a picture of Newland's periodic table. You can see that there are 1, 2, 3, 4, 5, 6, 7, 8 groups. And supposedly group 8 is supposed to have similar similar properties, okay? Here's the video. That's actually 2 videos. Let's check it out.
Welcome to educate.com. This video talks about Newland's law of octaves. The objective of this video is to understand John Newland's attempt to classify elements, Newland's law of octaves, and drawbacks of Newland's law of octaves. The attempts of Dobereiner encouraged other chemists to correlate the properties of elements with their atomic masses. In 1866, John Newland, an English scientist, arranged the then known elements in the order of increasing atomic masses. He started with the element having the lowest atomic mass, that is hydrogen, and ended at thorium, which was the 56th element. He found that every 8th element had properties similar to that of the first. He compared this to the octaves found in music. Therefore, he called it the law of octaves. Hence, it is known as Newland's law of octaves. In Newland's octaves, the properties of lithium and sodium were found to be the same. Sodium is the 8th element after lithium. Similarly, beryllium and magnesium resemble each other. It was found that the law of octaves was applicable only up to calcium, as after calcium, every 8th element did not possess properties similar to that of the first. It was assumed by Newlands that only 56 elements existed in nature and no more elements would be discovered in the future. But later on, several new elements were discovered whose properties did not fit into the law of octaves. In order to fit elements into his table, Newlands adjusted 2 elements in the same slot, but also put some unlike elements under the same note. For example, cobalt and nickel are in the same slot, and these are placed in the same column as fluorine, chlorine, and bromine, which have very different properties than these elements. Iron, which resembles cobalt and nickel in properties, has been placed far away from these elements. Thus, Newland's law of octaves worked well with lighter elements only. Even after the rejection of Newland's law of octaves, many scientists continued to search for a pattern that correlated the properties of elements with their atomic masses. In this video, you have learned: in 1866, John Newlands, an English scientist, arranged the then known elements in the order of increasing atomic masses. He found that every 8th element had properties similar to that of first. He compared this to octaves found in music. Therefore, he called it the law of octaves. Hence, it is known as Newland's law of octaves. Drawbacks of law of octaves. It was found that law of octaves was applicable only up to calcium, as after calcium, every 8th element did not possess properties similar to that of first. It was assumed by Newlands that only 56 elements existed in nature and no more elements would be discovered in future. Newlands not only adjusted 2 elements in the same slot, but also put some unlike elements under the same note. Thank you.
Well, I think that was not cool of him to assume that there would be no more elements after element 56. That was kind of weird, right? For scientists. As a scientist, we always think, okay, there's always going to be more and more discoveries. And for Newland to assume that at 56, that was going to be it, I think that was a little bit strange.
Our Earth is a collection of puzzle pieces that make up the universe. In the vast darkness of space, the universe is lit by stars, which could one day become a supernova and create all of the puzzle pieces that we know today as the elements. All elements were formed and released into space by exploding stars. For centuries, humans have tried to discover what makes up the world around them. Little did they know that all the pieces they needed were right under their noses. The discovery of these pieces revolutionized our understanding of the world and allowed for the creation of what might be the greatest gift to science, the periodic table. So, where are these elements, and how do we find a means to order them? Well, believe it or not, ancient civilizations were very much aware of many elements around them, but they did not identify them as the pieces of our universe. Elements like gold, silver, and copper were easily spotted by ancient cultures and were used for multiple purposes like jewelry and tools. Why were these elements spotted so easily? Think of the periodic table as a puzzle. The corner pieces or edges of a puzzle are generally the easiest to find and place because they stand out with their smooth edges and clearly don't interlock with other puzzle pieces. Like puzzle pieces, elements can be choosy on who they interact with. Some like to interact with other elements, while others do not. The elements that do not interact with other elements are easy to pinpoint, while the ones that like to interact with others are difficult to find. Gold, silver, and copper are some of the choosier elements, so we could find them easier. So let's fast forward to the late 1600s, where Hennig Brand, a German alchemist, was busy working in his laboratory. Like many other alchemists of his time, Brand was trying to extract gold from the human body. Brand hit upon what he thought was the most obvious answer to his problem: urine. Urine is gold in coloration and could perhaps have gold in it. So, Brand collected as much urine as he possibly could, much of it being his own, and he decided to boil it down in hopes of obtaining gold. So Brand boiled his, urine down until he collected a paste and heated the paste to a very high temperature. Eventually, smoke appeared and the material burned brightly and violently. Brand had unknowingly isolated phosphorus from his urine. This was the first time anyone had discovered an element, but he didn't really understand what he had done. At the time of Brand, the concept of an element had not been discovered. Instead, ancient Greek principles of objects being composed of earth, water, air, and fire were predominant. It wasn't until the work of Antoine Lavoisier, who is now known as the father of chemistry, that science defined what an element was. Lavoisier defined an element as a substance that could not be broken down by existing chemical means. Lavoisier created a list of the known elements of his time and tried to put the elements in some sort of order in which they could be classified, such as gases or metals. He was the first one to try to put the puzzle together. This was just the beginning of a means to organize the known elements of his time. Many other chemists then came along to make the puzzle clearer. One of them, John Dalton, weighed the elements and arranged the puzzle by weight. German chemist Wolfgang Doppelreiner later combined elements to see how they reacted with one another. What he found was that certain elements shared similar properties and reactions. For example, when pure lithium, sodium, and potassium are exposed to water, they will react violently and skid across the surface of the water with sparks. The scientists then realized that these similarities are no coincidence. Elements belong to families that share similar properties. But the chemist who finally put the puzzle together was Dmitry Mendeleev. He created cards of each known element and tried to order them based on atomic weight and their known properties. The story is that he stayed up 3 days and 3 nights, and he finally fell into a deep sleep and he dreamed about a table to order the elements. Mendeleev was not only able to create the periodic table, but he was able to predict elements that were not yet discovered. The puzzle of the periodic table of the elements was solved.
All right. So thank you, Mendeleev, because he is the one who gave us our periodic table. He's also going to be the next person probably we're going to be reading about because he did use some of that information from Newland and Dombringer to create that periodic table. All right. So let's summarize today's reading. Johann Dobriner organized elements in groups of called triads. And you got to remember that these triads why were they grouped? Because they had similar chemical and physical property. The second person to try to organize elements was Mr. John Newlands, and he proposed the law of octaves. And the law of octaves grouped or organized by atomic mass, and he noticed that every eighth element had similar properties. Okay, and both of them were both rejected, and they both had their faults as far as all the elements in the periodic table were concerned. They were not able to be put in triads or into the law of octaves. So let's do these questions together. Hold on, let me stop.